Welcome everyone to this week's M2D2 talk. This week we are joined by Andrew Campbell and Jason Yim. So Jason is a PhD student at MIT under Tony Akola and Regina Barzilay. And Andrew is PhD student at Oxford under Tom Rainforth. And today they're going to tell us about protein design and generative flows. So yeah, take it away.
Okay, great. Yeah, thanks for the invite. So today we'll be talking about our latest preprint, generative flows and discrete state spaces. And one of the impetuses for this paper was so that we could do multimodal flows and apply it to protein co-design. So yeah, Andrew and I will be discussing that. So kind of like just to set the stage of what problem we're tackling, we're talking about protein modeling and particularly how we want to do de novo protein design. And traditionally, this is the workflow, how it's been done. First, you start off by designing the structure in a de novo way, and then the sequence can be generated, conditioned on that structure. And then the last two steps, like virtual screening, experimental validation, these are just standard steps where we currently use tools like AlphaFold 2 or ESMFold to pick out the structures and proteins that we like, and then send them to the wet lab because that's like a costly endeavor. And one thing that we're thinking about is that like why do we have to like stick to this paradigm of doing structure and sequence in tandem? Like you could also start from a sequence and go to the structure. And so we want some sort of way to have flexibility in how we generate the backbone in the sequence and not be limited by the previous workflows. And so this is kind of one of the main things that we were going after with this paper was to have this flexibility. You can imagine that you might want to generate both at the same time for reasons like maybe a sequence should influence the structure and vice versa in ways that we don't know how, but the model should determine it. And so we call this paradigm to be co-generation, and other papers I call it co-design, but we call it co-generation because in our scenario, we're trying to generate both simultaneously rather than like just to generate modeling on one modality. So this is like one capability I want our model to have. And then there's also another paradigm where you might like have a structure that you already want and you want to do something called inverse folding, where you want to train a sequence that will fold into that structure. So here you give the model the structure that you want and that stays fixed throughout. But then for the sequence part, you give it noise and the noise gets iteratively denoised until it becomes like the sequence that you want at the end. And the third paradigm that we're going to talk about is called forward folding, where you know the sequence that you want and you kind of want to like predict the structure for that or like generate it. And you can also do just sequence or just do structure generation with this as well, but that isn't like as useful in many contexts. So these are like the kind of the three disrata that we want the model to be able to do. And so like some of our previous works have tackled the problem of the structure generation portion. Things like RF diffusion, frame diff, frame flow. We found that like doing things like SC3, also like full flow, yeah, they work really well. So SC3 diffusion and flow, just diffusion and flow matching methods like work pretty well in the structure space. But for sequence generation, the answer of what works the best in the protein context is a very unclear. And so this is what we set out to solve with technical contributions of this work. So to give like an outline, like we were thinking about, like, okay, can we just like take off the shelf methods? Like you might say autoregressive, that's been really popular in NLP. But then the question is like, how do you connect this with the continuous modality where we're doing diffusion and flow modeling? And then that might naturally lead you to consider diffusion models, but they want them to be in continuous time to be in sync with how the structure is also being denoised. And Andrew, my colleague, like he worked on continuous time diffusion, discrete diffusion models, and him and other people found it to be like a little bit too cumbersome. And so this is what led to our solution was to do flow matching, which we've seen in the diffusion framework that it really simplifies how you do generative modeling in continuous spaces without loss of performance. And it simplifies the implementation as well in the continuous space. So we set out to try to figure this out in the discrete portion of how to apply flow matching there. So this is going to be the talk in the next like 40 minutes. Like we're first going to talk about discrete flow models. Andrew's going to take over that to talk about how we developed flow matching in discrete state spaces. And then as kind of like a toy example, we're going to show how it works on text. So it can compare to other methodologies in like a pure just head-to-head comparison. And then we're going to show how we extended discrete flow models to be applicable in protein co-generation. And this is what we call multiflow. So I'll come back to talk about how we've extended discrete flow models with our previous work on structure flow models. So with that, I'm going to let Andrew take it away.
Yeah, so I'll be going over how we defined our flow model to do generative modeling on discrete state space. So at a high level, what we're aiming for is some kind of process that, in the same way diffusion, it starts at a noise distribution and then gradually morphs that into a data distribution. So at time 0, our marginal distribution over our state xt should be purely noise, and then at time 1 should be distributed according to the data distribution. So the first question is, how are we actually going to define this interpolating process that starts at noise and then goes to the data distribution? And the second question is, okay, once we have defined our desired like flow in that probability space, how do we then actually make a stochastic process that we can then simulate to actually do generative modeling and simulate along the process that has those desired marginal distributions? So to tackle the first question, this is where we take some inspiration from flow matching, and we're going to define our interpolating process from noise to data as a mixture of conditional processes, conditional on some data point x1, and then our unconditional process or our unconditional marginal distributions in green, and then the expectation of that conditional distribution with respect to the data distribution. So to give you an idea of what that looks like, if we have a conditional distribution that starts at noise, then it's going to gradually concentrate into just a one hot vector on the conditional x1 point. And so I've written the equation here where at time 0, it's just uniform, and then at time 1, it's a one hot vector on the conditional data point. And then if you then take the expectation of that with respect to the data distribution, you precisely get that desired flow in the distribution space that we were after, where it starts at noise and then gradually interpolates towards the data distribution. Because if you take the expectation of that one hot vector with respect to the data distribution, you just get back out the data. So this is how we can define a gradually interpolating process from noise to data as this mixture of simpler conditional distributions. To give you another example, if we instead define our conditional distribution to be a mixture between a mask state and the one hot vector on x1, then at time 0 it's just one hot on the mask, and then that gradually interpolates towards a one hot on the given x1. And then when you take the mixture and you take the expectation with respect to the data distribution, you get a different type of interpolating process where it starts all on mask and then it just gradually reveals the data distribution. So there's some flexibility in how you can define your interpolating process, kind of depending on what your data looks like. So this P of xt given x1 is just something you will define when you're building your generative model. So the second question is, how do we then create a stochastic process that is going to go through all those marginal distributions that we just defined so we can actually do generative modeling? So we're going to use the language of continuous time Markov chains to find a stochastic process that gets those marginal distributions. And a continuous time Markov chain is a stochastic process with discrete states. So in this case, it's 1, 2, or 3, and then it's continuous in the time variable. So following a trajectory, what that looks like is a particle will start by just sitting in a state for some amount of time, and then after a certain amount of time, it will jump to a randomly chosen another state, sit in that state for some amount of time, jump to another state, sit there for some amount of time, and continue this process. And the quantity that is defining the dynamics of this continuous time Markov chain is this rate matrix that gives you between two states A and B, what is the rate of transitions between state A and state B. So to understand, like, okay, what exactly is a rate? Well, it's just, if you imagine you're going to simulate your stochastic process in the next time step dt, then this rate matrix from A to B, or the AB value of that rate matrix multiplied by that time step dt is the probability that you're going to transition to B, given that you're currently in state A. So the take-home message from this is the rate matrix is the quantity that fully defines the dynamics of this continuous time Markov chain. And if you have the rate matrix, then you can just like do this dt integration steps and simulate the continuous time Markov chain. So what we want to do now is find the rate matrix that is linked to those marginal distributions that we just defined earlier. And the Kolmogorov equation is the equation that allows us to link rate matrices to marginal distributions. And the Kolmogorov equation is just a continuity equation in discrete state spaces, where it's just looking at the difference between inflowing mass and outflowing mass. So the inflow mass in orange, if we're looking at focusing on state xt, then you're just summing over other states j and looking at the rate from j to xt and multiplying that by the marginal distribution of state j. And that gives you the total orange incoming mass. And then you look at the outgoing mass. So you look at the rates from xt to other states j and multiply that by the marginal distribution of xt, and that gives you the total blue outflowing mass. And then the difference between these two inflows and outflows is the rate of change of the marginal distribution at time t. So yeah, I've just rewritten the Kolmogorov equation here, and then we can make a definition for the diagonal entries on the rate matrix. It's just a definition that makes things easier. And then you can rewrite the Kolmogorov as this very simple ODE in probability distribution space, where the rate of change of the probability distribution vector, where it's just like each entry in that vector is just the probability of each of those individual states. The rate of change of that vector is just the rate matrix applied to the marginal distribution vector. So this gives us an ODE, or like a flow in probability distribution space. Now the question is going to be, okay, so we have a marginal distribution that we defined earlier as expectation over some conditional distributions that we defined. What we want is the unconditional rate matrix in green that satisfies the Kolmogorov equation for that marginal distribution that we defined. So the insight is that this green rate matrix is hard to get directly, but we can get it by going through this intermediate rate matrix in pink. So this intermediate rate matrix is conditioned on x1, and it satisfies the Kolmogorov equation for the x1 conditioned marginal distributions. And we can see later that this is a much easier to find rate matrix.
There's a question in the chat.
Yep.
I think regarding the last slide, asking why RT could be rewritten in this way.
Why RT can be written like this?
Yeah.
So the off-diagonal entries of the rate matrix just have to be greater than 0, and then you define the diagonal entries to be the negative row sum on each row, and that's just a definition, and that helps you make this clean way of writing the Kolmogorov equation. Yeah, but it's just a definition, and the only constraint on the like off-diagonal entries is just they're greater than or equal to 0.
I think that makes sense. Thanks.
Yeah, so we have a result that if you know this conditional rate matrix that satisfies the Kolmogorov equation for the conditional marginal distributions, then you are able to calculate the unconditional rate matrix by taking the expectation with respect to a denoising distribution. And the denoising distribution is something that is, you're given a noisy point xt, and you have to predict clean data x1, and you take the expectation with respect to that denoising distribution of your conditional rate matrix. So the first missing ingredient in this story that we've said is this denoising distribution. Like that is intractable to get for practical data sets. And so we're going to learn that with a neural network to do the denoising problem. And the second missing ingredient is this conditional rate matrix. I've said it's easier to get, and so we're going to try and discover that later on. But once we have these two ingredients, then we are able to calculate the green unconditional rate matrix, simulate the continuous time Markov chain with that rate matrix, and then therefore be able to do generative modeling going through that interpolating flow that we defined. Yep, so once we have those two ingredients, this is how we would actually sample from the model. You would just start at time 0 with a sample from the initial noise distribution, and then you would iterate these integration steps, where for a time t, you would have current state xt, you would calculate your unconditional rate matrix, and then you would take one step forward in delta t. And to do that, like we saw previously, the jump probabilities are just given by the rate matrix multiplied by your integration time step delta t. So you just sample from those jump probabilities, and then you iterate this process just doing these Euler integration steps in a similar way you would integrate a diffusion model. So to get the denoising distribution, we're going to learn that with a neural network. So it's just the cross entropy loss that is very similar to language modeling. So you would, to train it, you would sample data points. You would then sample a time level between 0 and 1, and then you would corrupt that data point using the conditional marginal distribution that you defined at that time t. So you corrupt it a bit, and then you predict logits on that clean data point from your neural network, and then train using the cross entropy. And giving you the examples we had before of what that conditional marginal distribution looks like, it's just some like linear interpolation between the noise and a one hot vector on the x1 data point. So it could either be interpolating from uniform or interpolating from mask, and these are just different choices you can make for your data. And the second ingredient was the conditional rate matrix. So like I said before, we obtain the unconditional rate matrix that we can do generative modeling with by taking the expectation of the conditional rate matrix with respect to the denoising distribution. And so, yeah, we have the Kolmogorov equation for the conditional rate matrix. And we know the conditional probability distribution because we defined it earlier on. And then we just differentiate that with respect to time to get the left-hand side of the Kolmogorov equation. So then we have the left bit and right bit, and we now have like the two vectors, but we're just missing this matrix in this equation. So the question is like, how do we get that matrix? So it turns out that this is under constraint. There are many matrices that will satisfy the Kolmogorov equation for some given marginal distributions, but we can just like write down by inspection a one solution to the Kolmogorov equation that is just like an analytic form based on time derivatives of the marginal distribution. That's something we can write down just like by looking at it and verifying. And this rate matrix satisfies the Kolmogorov, so it will give you those conditional marginal distributions, but it has kind of particular dynamics in that it has very few transitions in the trajectory space. Like a CTMC, the continuous time marker chain, will make very few jumps. So if we want kind of dynamics that have more jumps in them, we can like artificially add in some more rate into that process by adding in some amount of rate matrix that is in detailed balance with the marginal distribution. And then we can vary the amount of like extra kind of dynamics we're introducing into the process with this eta stochasticity level parameter. So the takeaway from this is like, we don't have time to go into the like full details of the maths, but it is analytically possible to write down X1 conditional rate matrices with some choice of like particular dynamics, and then we will substitute that in to that expectation with the denoising distribution, and then get a rate matrix that we can use for generative modeling. So to give you some intuition on that stochasticity level parameter eta, if we have zero stochasticity, then the process is achieving those marginal distributions with as few transitions as possible, like in certain cases. So in this like unmasking case, when a token gets unmasked, it will just stay unmasked because that's the solution that achieves the fewest jumps. So it will just continually be unmasking tokens, and just once they're unmasked, just leave them be in that state. But if we were to increase eta and introduce more stochasticity into the dynamics, then we have this kind of masking, unmasking type process where tokens get unmasked, and then they get masked again, and then they get unmasked again. And the benefit of doing this is that it gives the opportunity for the model to make changes as it's doing generations. So if it generates a word, and then later on it thinks, okay, this word doesn't fit in my sentence anymore, then it can get remasked and then unrevealed, revealed again, and then this time it can make it more consistent. So if we look kind of to the right of the middle, we can see that the model initially generates the word hill. And then later on, it decides that will actually fits the sentence a bit better. So this kind of dynamics allows the model to like make changes like that. And then we actually show in some text experiments that having non-zero stochasticity in your dynamics is actually beneficial. So in this experiment, we did unconditional text modeling. So just learning on chunks of text and then generating unconditionally some sentences. And then to measure the quality of those sentences, we take a large language model and look at the negative log likelihood that that large language model assigns to our sentences. And the lower that is, the better. But if you just repeat the same token over and over again, that can artificially make the negative log likelihood very low. So we also measure the entropy of our tokens in each sentence. So it's not just repeating the same token over and over again. We want that entropy to be as close to the data distribution as possible. So the good region of the graph is in the bottom right. And we can see that with the discrete flow model, with non-zero stochasticity, we're able to like get the closest to the bottom right portion than if we just set the stochasticity level to 0, then it's much more similar to like just autoregressive and absorbing state diffusion models. So like this kind of extra dynamics that we can play with is actually able to give us like boosted performance at sampling time. Yeah, so now Jason, you want to take over for the
yeah, so now I'll talk about the protein part and how we extend it to multimodal flows. So Andrew just described like discrete flow models. And so like I actually mentioned that we want to do structure and sequence code generation. And so the top part is showing how we do the structure generation using a previous paper called FrameFlow, where we develop SE3 flow models. And there's two flows to this. One is the translation of the frame, and then there's the rotation of the frame that both get denoised over time. So the translation is the canonical flow matching model on Euclidean spaces, whereas the rotation is an extension to manifolds. And then the amino acid part down here is sampling from the categorical distribution at every single time step, and also is following along this linear time schedule. And it's using exactly the formulation that Andrew went over in the discrete flow model case. So the cool thing here, I think, is like we have a flow on Euclidean space, one like a manifold, and one on the discrete space. So these three different flows will capture how a protein is generated. And another thing to take notice here is that we introduced two timescales. So for the translation, we have this T that controls how the structure is getting denoised. But then in the amino acids, there's a T tilde that controls how the sequence is getting denoised over time. And so there's interesting tricks that you can play with these two timescales for protein generation. So here's like an animation of how the generation happens. You can see over time, both are being generated simultaneously and sync with each other, so that they, at time 1, they both end up becoming a sample from the data distribution. So to like emphasize more on this the time component for the structure part, this T, this regular T controls how much noise is in the structure, and then this tilde T is controlling going from noise to data in the sequence portion. And so to have control over this, we can have flexible sampling at sample time. So using just a single model that's trained over all the T and T tildes, we can do code generation by starting the structure and the sequence by setting the T's to be 0, and this corresponds to noise. And then you just let T go all the way to 1 using a different schedule, but here we use a linear schedule, so they're both being denoised at the same rate. And for inverse folding here, because you want the structure to start from data, you would set T to be 1, and then let the noise just go from 0 to 1, so that the sequence is only denoised while the structure stays static. Forward folding is then the opposite, where the sequence is constant, so like that stays fixed by setting T tilde to 1, and then the structure is what gets denoised, and that's what T goes from 0 to 1. So to be able to use a model like this at sampling time, you have to train it in a way that it's seen every combination of noisy sequence and structure. So that's what we call decoupled training. So the thing to note here is like the expectation is taken over like a uniform sample of T for the structure and T tilde for the sequence. So we call this decoupled time. It's like you can imagine like a 2D grid of the time, and we're trying to sample across this whole grid so the model learns every possible combination of how much noise is in the structure and the sequence. And these two terms here are the structure losses. I'm not going to go over them in detail. We have a previous paper called frame flow that goes over how these are formulated. But you can see here that the T that goes in here is oh, actually it also contains amino acid, but it sees both the noisy sequence and the structure. And then this third term is the amino acid cross entropy loss that Andrew previously went over.
There's a question in the chat.
Yes.
Prudencio is asking, why is the time decoupled? There should be consistency between structure and sequence at all time, maybe.
You can couple them. You can do that, but then when you want to have flexibility in sample, you can only do the top one here, which is cogeneration. So here, T and T prime will always be the same, going from noise to data. But we also want the capability to do inverse folding and forward folding by like fixing one of the times to always be one here. But then there's also other cases where you like might want to like do partial denoising, like you might want to partially denoise a structure and let the sequence catch up and do it like that. So by decoupling time in the training objective, you have flexibility in being able to sample with any rate of structure and sequence and any sort of protein generation task.
Can I follow up quickly? So
yep.
I agree that you give flexibility, but on the consistency perspective, yeah, how do we ensure consistency between the structure and the sequence at on time?
Yeah, so we played around with several schedules, and we found like the model is able to handle it basically. Even if we train it with the like decoupled way, the model can still handle the T's being the same throughout. And I think I was also surprised it could handle that, but it does pretty well at keeping the structure and sequence consistent, even though it's learning across this whole grid. Yeah, that answers your question. Like the answer is like it just kind of works out in the model performance empirically, like we've seen. And yeah, we tried both options, like keeping T and T prime the same during training, or like doing this decoupled thing, and there wasn't a loss of performance for the generation for all the tasks. Yeah, so 80% of the time we train with this both loss. But then in inverse folding, because in inverse folding T is set to be 1 throughout, and like you have a very low probability of sampling 1. So we keep T fixed to 1 while letting the structure just be sampled from the uniform distribution. And then the other 10% of the time, you do forward folding where now here the sequence is fixed by setting T prime to be 1, and then you just sample T from the uniform. So this is like a way to train a model on all 3 tasks, but like we're not fully doing each task individually. So for protein experiments, we use the dataset that I curated in FrameDiff. Like we only took monomers and we made sure like there were high quality proteins with less than 50% loops. So like they're very stable. And then the length of the proteins was from 60 to 384, and this resulted in about 20,000 proteins. So the main task we wanted to tackle was generation, but then because of the extra capabilities of our model, we wanted to also explore forward and inverse folding. But these were kind of like secondary results that we plan to like follow up in future works, and were just like something to explore very rudimentary in this paper. So for generation, we follow the RF diffusion benchmark where they sample 100 backbones of these 4 lengths, and then we just pass the designability, report the designability as well as like the standard diversity and novelty metrics. For inverse folding and forward folding, we didn't have time to like do a very rigorous comparison here. Like for instance, take the CAS split and evaluate on those. So we used a time-based test split to take a subset of proteins that were after the cutoff for the PDB dataset that we downloaded. And so this resulted in like around 450 structurally distinct proteins that we evaluate on for inverse and forward folding. And for inverse folding, we just do designability, and forward folding is the RMSD as the metric. And so designability, in case people aren't familiar with it, is that you will use your general model to sample the backbone and then have some sort of way to get the sequence out. And then the sequence will be fed into a accurate protein folding, forward folding network like ESM fold or AlphaFold 2. Here we use ESM fold just because it's very easy to run. And then the success is if like the global average RMSD after alignment is between 0.2 nanometers. And then the RMSD between alpha or the folding structure and the generated structure is called SC RMSD throughout. So for sequence design approaches, we compared 3 different ways to calculate designability. One is using co-design 1, where our model, for instance, you can generate both the structure and the sequence. So we use these in designability calculation. But then the question we wanted to see was like, how is this compared to the de facto way everyone does it? Everyone right now uses protein-PNN to generate the sequence conditioned on the structure. So our hypothesis was to see kind of if co-design, like the sequence for Multiflow, could beat protein-PNN. So here, although Multiflow generates both the structure and the sequence, we throw out the sequence that Multiflow generates and use protein-PNN to predict the sequence for us here. And we use that in designability calculation. The one that's actually used in the field the most is where protein-PNN will sample 8 sequences, and you take the best one out of those in the designability metric. So I will refer to these 3 like scenarios of how sequence design is done as co-design 1, protein-PNN 1, and protein-PNN 8. So when we first like ran this model, like the initial experiment, like after checking for bugs and whatnot, was that there was a pretty big gap between our sequences and protein-PNN sequences. In particular, protein-PNN's designability was almost double that of our model, like what was coming out of Multiflow. And so this like spurred a lot of like investigation. And like one thing that we found was that actually the wild type distribution that you get from PDB is not so good. In fact, only 70% of the sequences of the wild type are designable. 30% of them that we're learning on actually will never pass this metric that we set for ourselves. And so, yeah, we saw this issue and we saw how to improve that. One thing that's been reported in the literature a lot is that when you use protein-PNN to like refold the sequence, get the sequence out from the structure, is that this has way higher stability than the wild type sequence. And it's worth noting that like protein-PNN, it's a highly regularized model to not overfit, because the more it overfits, the worse the designs are for the downstream tasks. So what we did was like we took our whole data set, we actually ran protein-PNN, and then we calculated like the designability, like the SC RMSD metric. You can see that there's this big shift to the bottom right, which shows that protein-PNN sequences have much better designability than the wild type sequences that are out from the PDB. There are even some that like the structure that ESM fold predicts is way different from the wild type structure, like some of the sequences that are in the 10 RMSD range. So protein-PNN is able to like really rescue those and give you designable sequences. So what we do is something called redesign, where we instead train on the protein-PNN sequences rather than the wild type. We first regenerate the sequence for every structure, and then we use the protein-PNN sequence or keep the wild type depending on which one has the lower SC RMSD. And now we have like a very high quality data set that's very aligned with the metric that we're evaluating ourselves on. So yeah, now not over 90% of them is designable. So
there's a question in the chat.
Yeah.
From Ella asking, when you discard the sequence generated by Multiflow, are time for a sequence and structure decoupled?
No, so in that case, like both of them are generated, like the model will generate both the sequence and the structure. So like in that case, like they're coupled. Although it's like not trained like that, but during inference, it's sampled in a way that they're both coupled. Yeah.
Thanks.
Thanks for the question. Yeah, so then this kind of raises some red flags to ML people, because we're optimizing an artificial model that would have like a lot of adversarial examples and maybe not be so robust. So this should like raise some alarms in people's brains when we're doing this. And so like one interpretation of what we're doing is that because we know protein-PNN sequences are stable compared to wild type, we're biasing our sequence, or like the sequences for Multiflow, to also be more stable. And so like a pro of this is that generally in protein design and engineering, you want more stable proteins because you can have like more mutations and potentially improve the fitness of the protein. But then there's also this other con of stability, in that like there's like enzymes and like condensate, like intrinsically disordered proteins that rely on this on instability to function. So you actually lose some function if you optimize for stability. And so this raises a question of like, what do you want to bias your sequence towards? Like in this paper, we chose stability, just because protein dependent was very easy to like scale up. But it's like an interesting question of how we can guide the sequences towards other properties using this sort of technique. So like because redesign actually worked pretty well for us, and I'll go over to numbers later. Like we were wondering like what happens if you actually train on synthetic data from like the actual generative model itself. So we call this section synthetic data distillation, where like after we trained a multi-flow model, we then sampled a bunch of proteins, like around 20,000. We just uniformly sampled the lengths, and then we took the subset of those that were passing designability. And then from those, we clustered them, and then we found like about 4.2 thousand next synthetic proteins that we could like add to our training set. And these proteins, the novelty was like they were similar to the training set, but there was like still some conformational differences in them that we hypothesized would still help the model kind of generalize beyond the training set. So this is like what we sought to do with distillation. And then now when we incorporated this redesign of the sequences and then incorporated the synthetic data, we found an almost double in the boost in performance of Multiflow. In that like below we were getting like 0.41 in co-design metric, and now we're getting 0.88. And this is in fact on par with protein-dependent one. So like after distilling protein-dependent sequences into our model, we're getting as good sequences out from protein-dependent. And so you might be asking like, okay, you just recapitulated protein-dependent in your model, but now we just have one model to do both sequence and structure generation at the same quality as protein-dependent, rather than the two-step process. And so you can imagine this leads to a lot more flexibility in doing multimodal training and inference. And then after we did this, we compared to other co-design methods out there. So there's like Prod-Perdel, that's from Stanford, and a protein generator also from Baker's lab. And we find that our model is able to get a much better co-design one performance. So like in Prod-Perdel and protein generator, they also generate both the structure and the sequence. So we ran that evaluation again with our designability calculation. And also another thing to note is that we also get way higher diversity than those numbers. Much more structurally dissimilar proteins to come out. And then the other thing is like our diffusion of how we compare to that. So we found that in the protein-dependent metric, we're also able to improve upon our diffusion. And then even in the protein-dependent one metric, we're also able to improve upon that. We can't compare co-design one or our diffusion because our diffusion does not give you a sequence. That only gives you a structure. And so like just I'll say again, this is all condition generation. And condition generation is like a follow-up work. The other thing that we looked into was forward and inverse folding. And again, this was kind of like an auxiliary task in our paper. Like the co-generation was the main task. We compared to protein-dependent on this time-based split of PEB that we just curated. And we found that the RMSD to protein-dependent was quite similar. So like Multiflow is able to get around like 2.2 RMSD, whereas protein-dependent gets around 1.9. So I'll consider that to like not be statistically significant. And so they're similar in inverse folding. But for forward folding, we found that we do very poorly compared to ESM fold. And so this is something that we're aiming to improve the forward folding result of this general model. I mean, you can imagine that ESM fold was trained on a lot more data. It has access to like evolutionary information as well. So so much incorporate like evolutionary information into Multiflow would probably boost up the forward folding performance a lot too here. And I mentioned like all our results in this paper were on unconditional backbone generation, which is not really useful for protein designers. But like next step is that we're looking into doing multi-scaffolding and some other condition generation works. So I actually have we actually have another preprint out that explored multi-scaffolding with these the structure flow matching method. So you can imagine that now we can incorporate the sequence, and now that should hopefully improve the multi-scaffolding results across different classes. So just to close, we developed like Multiflow so that we can now do generative modeling on both continuous and discrete data. We tailored it to proteins, but it's entirely possible to extend this to like video, images, small molecules. I think the framework is general enough that it doesn't have to be very specific for proteins. But for proteins itself, there's a lot of different tasks that one might want to do. You might just want to do structure sequence generation by themselves. There's and then we discussed inverse and code generation and forward folding. And like what we're proposing is that you don't need to have a single specialized model for each of them, but it'd be great if like a model could be able to do all of them. And so our framework allows this sort of general purpose model for all these tasks just by doing tricks with like the T's and the coupling of the structure and the sequence. So yeah, happy to take any questions.
Oh, great. I guess I'm going to read some chat questions. Maxwell's asking, in code generation, do you find that the sequence settles before the structure?
Actually, the opposite. I think the structure settles before the sequence. So we actually had something called like an exponential scaling of the rotations that was figured out by Joey Bose and the Mila people. So like the structure does get set a lot before the sequence, and the sequence can follow it. We were exploring some ways to maybe like lag the structure behind the sequence and vice versa, like more explicitly, but we found that not to be really beneficial in this case. But yeah, having a structure be a little bit ahead because of the exponential scaling on the rotations makes it a lot better.
Yang is asking, I thought protein MPNN was trained on natural sequences without synthetic data. Do you have any ideas why protein MPNN can be trained on natural sequences and learn to generate more stable sequences in the first place?
Yeah, so my hypothesis is that protein is a heavily regularized architecture. It's really small. I think it only has like 200,000 parameters. But if you want to do structure generation, you need a much more expressive model than that. And so our model is based off attention and like IPA, and it also does like a global attention over the whole protein. So like I think what we found is like our model is very like learns the data distribution much more well than protein MPNN, because protein MPNN is actually not learning data distribution that well. It's learning like this inductive bias from the small set of proteins and the architecture design that's letting it generalize and get more stable proteins. So it's something that I was wondering too. My guess is the architecture, and yeah, it's just the architecture that's making it different. But it's something that we're thinking about. And distillation was like a necessary evil to make this work, but yeah, looking into ways to maybe remove that if possible.
In continuous flow matching, one can use approximate optimal transport based on mini batches to get better and smoother data noise mappings. Is it possible to do similar things for the discrete flow matching component here?
Yeah, so I think there is kind of like fundamentally more difficulty in trying to define these couplings on discrete spaces. Like when you say have an all mask state as your noise distribution, everything's just a mask, then you have like the same noise vector assigned to every data point. So it's kind of that will be quite difficult because there's literally just one noise type. So you could imagine doing some uniform noise and then trying to find some coupling there. But because of this like discrete nature of the state space, there's this like just inherent like jaggediness in how you can try and define that link. So it might not, well, it's not possible to define just like one deterministic mapping between these two discrete distributions. So you're going to have some stochasticity there, and it's going to be quite difficult to try and learn that. But I think that's a very interesting like future direction that I'm personally quite interested in as well.
I was asking, although the framework is general, I'm concerned by the fact that a lot of the work had to be put into making the sequence more designable using data distillation and so on. Do you expect this type of challenge to also appear on other domains of application, or do you think it's a protein-specific challenge?
Yeah, I can comment on this too. I think it's protein specific in that here, the actual data distribution that we're training on is not aligned with what protein designers want. As in like, in de novo, you want to go away from natural sequences and you want like more stable sequences than naturally occurring proteins, because like evolution doesn't pick for stability as well. So there's this inherent bias in protein sequences that I think this is also another reason why previous methods have failed to kind of incorporate co-design and code generation together. Some of these tricks will be kind of necessary. And I mean, in natural language too, it also pops up. the like ChatGPT is heavily reliant on aligning with human feedback rather than just taking things from the internet where you get like toxicity and racism in there. So there's like this similarity in NLP as well that I see.
Yeah, I don't see any like fundamental limitations in the framework because you know, we tested it on like just raw discrete data on this test experiment, and you know, it can perform just as well, if not better, if you know, tune these sampling parameters as say like your discrete diffusion models. So you know, I think that the framework itself has the flexibility to model kind of any kind of discrete data you want, and then attaching that to this continuous modality, getting these like multimodal models. But yeah, I think it's more of like a protein specific case that that here, you know, we really want to augment to a certain subset of that data distribution that is designable.
Follow up from Maxwell about the structure settling first. Interesting, since sequence seeks to mostly define structure, perhaps related to why the folding accuracy is lower, I wonder what relationship your model is learning. Is that something you've looked into?
Yeah, that's a good question. Yeah, that's something that we haven't looked into yet. But I mean, the forward folding, as we went over it, is like the weak link in this model. So like we're looking into how to improve the forward folding. That's going to involve investigation into what the model is learning in during training. Yeah.
Peter is asking, would it be possible to fine-tune the model to generate a specific kind of protein? For example, to generate knotted proteins, protein whose backbone entangle themselves in a knot.
Could you repeat the last thing you said?
Yeah, so for example, to generate knotted proteins whose backbones entangle themselves in a knot.
Oh, yeah. So I think the nice thing about this framework is that you can like use connection generators or like what I'm saying, like classifier guidance on the sequence, and that should affect how the structure is generated too, because they're all in one frame. Like if you're doing it in the previous way, then like trying to incorporate sequence into the structure part was difficult because you used a second model to generate the sequence. So I think one of the good things about this like all-in-one general purpose single model is that you can like incorporate conditions on both the structure and the sequence. So I think that's something that's really interesting to think about. I mean, I don't know what conditioning the particular proteins that the person was asking about, but if it's like a sequence condition, you can apply that. If it's like a structure condition, you can apply that. If it's both of them, then you can also apply them in this framework.
Any other questions from the audience? I have one.
Yeah.
So I guess this is my GPhonet brain overfitting, but there's like a noising operator that's implicit in all these things. Do you think that's something that could actually be learned or kind of inferred from data that would kind of help guide then the denoising that's learned?
Yeah, I had like some initial experiments trying to learn some kind of more meaningful way of corrupting the data set to get, you know, to your point xt, and then, you know, you use your model to try and reverse that. I think it's just I personally think it's kind of an open question in the community of like, what is your desired properties of such like a corrupting process? Like, you know, you need to somehow kind of learn the like meaningful factorization in some abstract sense of how you can go from the data distribution to the noise. And it's, you know, it's not only that you want it to be smooth, but like you also want it to be such that, you know, your network can generalize. Like that's the end of the day, what the thing you were interested in. So I think it's an open question, like exactly what properties do we want in that corruption process to enable, you know, raw sample quality that is different to the data set. So, you know, whether that is smooth in some sense, maybe, but yeah, I think it's a really interesting question of, you know, what kind of objectives, what kind of things are we looking for if we're going to learn that like noising operator.
Makes a lot of sense. There's new questions in the chat. So Inji's asking, I think the idea of redesign is cool, and achieving higher designability with redesigned sequences show the model's capabilities. But protein MPNN having higher designability can imply something different than higher stability. For example, LLMs favor LLM-generated text. Curious if this is applicable in protein MPNN and PLM case.
Can you say the part about LLMs? Like, what do LLMs do, or like
So
summation?
yeah, LLMs favor LLM-generated text.
Yeah. So with redesign, I think like because we're using ProTip and ESM folds in the loop to generate the training set, like this also sparked off like warning signs in my brain, like you shouldn't be doing this basically. We did do some external validation, like using AlphaFold instead to fold these sequences, and they're still able to get high designability. So we got some like independent models to like test out whether we were just like overfitting onto like the protein sequences. And I think it's like brings up a broader question to the community, which is like we have this metric of designability that everyone uses, but it's the only metric, and I think we're all now overfitting onto it. And so we need more metrics that we need to be able to test the designability metric and stuff. So it's not something that we like explored in this paper, like nor was it our goal to explore that, but like definitely in the future, because I think now we're approaching designability metrics that are above 90 and stuff. So we really need to like evaluate, revisit this and see if there's other metrics to do. But yeah, so the answer is like, I don't have a good sense of how much, because you actually never experimentally tested these proteins. We'd actually have to experimentally test them to answer that question if it's just learning things that protein likes, but wouldn't work in nature. So yeah, fortunately, outside the scope of this paper.
Someone is asking, maybe this is a stretch, but do you think this could be augmented or fine-tuned for molecular conformer generation?
Yeah, I definitely think so. Like there's maybe an idea like pre-training on all of these tasks could make it like be better at like confirmation generation as well. Like the forward folding arrow here, I actually view it more as a confirmation generation. That like if you can learn the code generation inverse folding well, then maybe that'll help out in getting more diverse structures out from a sequence. So confirmation generation is something that's very applicable here. You should definitely go check out like AlphaFlow from Bo and Jing, also from my lab. Like he directly tackled confirmation generation. Like maybe or maybe not. Like we're thinking about combining the two. But yeah.
Cool, thanks. Julian is asking, for bound state co-design to bind another protein, what could be the multimeric analog to the designability metric? Can the designability metric be improved by integrating the folding/inverse folding model confidence instead of just the similarity in RMSD? Any general thoughts on how, or maybe you can answer that first and then I can follow up.
Yeah, so if I understand correctly, you're kind of wondering like how do you extend designability to multimers? I think there's a paper from the Baker Lab by Nate Bennett of like improved binary design with deep learning. So there they also had this designability metric of using AlphaFold's PAE point alignment error metric, which is also like some sort of confidence metric to show like how tightly it will bind, and also incorporating the confidence of the interface, I believe. So they found that to be like a decent indicator of binder success. I think I'm still a little skeptical. Like AlphaFold multimer, for instance, is not so good at like binder proteins, and so we need better prediction models for binders and multimers before we can have like a very like reliable model. But it's all a question of how you can do it for multimers and binders designability.
Yeah, the rest of the question was just like any general thoughts on how we can find in silico metrics that correlate better with lab experiments.
I think a lab just has to develop the virtual screening method and then test them out on like a wide class of proteins, basically. I know not everyone has like the compute as like David Baker or like Gabe Rockland to just high throughput on everything, but like people should be like reaching out to them and like saying, I have a machine learning idea. Reach out to their collaborators, be like, can I test this out? And if like the grant allows it, then maybe they can strike a collaboration. But it just needs to go end to end to develop the method and test it out before people start using it for real.